Hi guys, welcome to tutorial 7, question 2. Let's do this. Alright, so like always, I want to put the question right over here. Read it over yourself. Yeah, there's two parts to this. So read it over yourself, attempt it yourself, and then we'll go through it together. Alright, so looking at the question, the first thing that they want to ask is that what does this function do, and state the preconditions and the postconditions for this function. Alright, so the precondition is that a is an integer that's bigger than or equal to 1, right? And the postcondition, which will also explain what this function does, is that the function returns a squared, the square of a. So if you try that yourself, giving it examples and run through them together, you see that this mystery function, if you give it a, it will return a squared. Now, looking at the part 2, it says prove that the function is correct using loop invariant and variance. Okay, prior to starting the loop, right, before everything starts, you can see that in lines number 5 and 6, we say that I equals to 1 and b equals to 1, right? Substituting these things into our invariant, the loop invariant being I has to be between 1 and a inclusive, so including them, and then b has to equal to I squared, that's our loop invariant. Substituting the numbers that we already have, I being 1 and b being 1, we know that, okay, fine, is 1 between 1 and a inclusive? Yeah, it is, because 1 equals to 1. And, alright, is b equal to I squared? Well, we know that b is equal to 1, and we know that I is equal to 1, so 1 squared equals to 1. That checks out. So the only thing to prove here is that 1 is smaller than or equal to a, and that holds by the precondition that we just spoke about. And yeah. Now, we just proved that for the beginning, right? But let's say, I mean, you can see the while loop at line 7, but let's say as we're going through this and we're at some random number, some arbitrary thing, right? We got to prove that at some arbitrary point, right, that this holds at the end of that iteration. The fact that, you know, let's say I subscript 1 is between 1 and a, I subscript 1, and that b subscript 1 is equivalent to I subscript 1 squared. I want to put it here because I keep saying subscript 1, right? I say, you know what, I'll say I1 and B1, just to make things simpler. Basically, I1 has to be between 1 and a, and B1 has to equal to I1 squared. And we must make sure that this is true by the end of that iteration. Alright, before we get into getting into proving this, that this thing holds by the end of it, let's look at a loop body, right? We know that I1 is equal to I0 plus 1, right? Because look at line number 9. Every time in the loop, that's what happens. So I1 equals to I0 plus 1. And we know that B1 is equal to B0 plus 2 times I0 plus 1. And that's how we get our new value for B1 if you look at line number 8. Now, why didn't we say 2 times I1? It's because I gets updated after B does. So we're still using the old I in our loop iteration. That's why we're using I0 rather than I1. And, you know, we also have that by the loop condition that I0 has to be smaller than A if you look at line number 7. Because if it wasn't, then it wouldn't go into the loop. So we also know that. Now, let's look at the loop invariant. We're going to break it down to 3 parts. I know it looks like 2 parts, but let's break it down to 3 parts. One being that we have to prove that I is bigger than or equal to 1, right? The second one being that I is smaller than or equal to A, and the third one being that B equals to I squared. Now, let's start with the first one. We're going to prove that I1 in this scenario is bigger than or equal to 1, or in other words, right, I0 plus 1 is bigger than or equal to 1. But that holds already because we know that I0 is bigger than or equal to 1 by the invariant, right? So therefore, I0 plus 1 is of course going to be bigger than 1. So that's the first one. The second one being I1 is smaller than or equal to A. Well, we already know that I1 equals to I0 plus 1, right? So we're, in other words, saying I0 plus 1 is smaller than or equal to A, right? By the loop condition, right? By the loop condition, we know that I0 is smaller than A. So in another word, can I say that I0 plus 1 is smaller than or equal to A? Yeah, I can say that. I just added that equal sign and it still makes sense, right? Because all of that can be shifted to the right. And that's for our case number 2. Now for our case number 3, where we want to say B1 equals to I1 squared. Okay, so we know what B1 is. B1 is B0 plus 2 times I0 plus 1. That's from the loop body, right? Now, B0 is equal to what? We know that B0 is equal to I0 squared, right? We know what the post condition is. This is supposed to square everything, right? And if we think successfully, that's what that's what it does every time, right? So we're going to rewrite it. We're going to say I0 squared plus 2 times I0 plus 1, and we know that by the invariant. If you remember, your high school calculus or just a basic stuff, you know that you can change that and factor it down. So we're going to say it's going to be I0 plus 1 squared. When you expand that, you're going to get the whole I0 squared plus 2 times I0 plus 1. And, I0 plus 1 squared, well, what's I0 plus 1? It's I1, right? So it's going to be I1 squared by the loop body. And now we know that if the loop terminates, we know that I is going to be between 1 and A inclusive, and B is going to equal to I squared, and that I is bigger than or equal to A, right? In another word, I is equal to A and B equals to I squared. Or, to even more simplify it, B equals A squared. So at the end, at line number 10, where we're returning B, that's correct. Now, if you take a look at page 54 of your notes, it talks about loop invariant, and then it gives you more insight of what's going on and a little bit more clarification that I think is going to be really helpful to you guys. So maybe definitely check that out. All right, guys, that'll be all for this question number 2 for tutorial 7. I'll see you guys in the next one.